All right. Good morning, everyone. Welcome to the second TLS session. If you're not here for TLS, you should stay anyways. Can you go to the next slide? Apparently this isn't working. Here's a note well. You may have seen this many times so far, so please note it well. Do we have a minute taker for today? Patrick, thank you. JavaScribe. Oh, thank you, Jonathan. All right. Blue sheets are going around. Please make sure you sign them. To reiterate, in discussing various issues and raising comments, please be professional, be polite, be succinct at the microphone, and state your name to help the minutes taker and JavaScribe. So this is our agenda. We're going to start off with a quick update in details 1.3. Some quick bashing to, we're going to reorganize and put the return reachability check and the connection ID draft after ESNI, and then go through a bunch of individual drafts that have been brought to the working group for discussion. So we went through this earlier this week, so there's no change here. And same. So, all right. I guess we can just get started with details 1.3. There are no slides. To just give everyone a quick update, David Benjamin, some very helpful comments and review of the draft, which were incorporated in the latest update from Ecker, all of which, there's one outstanding issue I believe Ecker wants to quickly comment on.
Yeah, so I think I got all David's issues. There was like one editorial issue which somehow I managed to lose and can't find again, but if someone finds it, I'll fix it. It wasn't major. The only outstanding technical issue is that the question of whether we should attempt to produce key separation between TLS 1.3 and DTLS 1.3. So to recap, in TLS 1.2 and DTLS 1.2, I believe, do not have key separation because they don't include a transcript in the hashes. In Quick, what we did was we did leaf key separation, but not internal key separation, so that the internal derivations are the same. My intuition is we don't need this for DTLS 1.3 because we hash the whole transcript. The transcript will be different because although the version numbers are not different, the entire handshake messages get marshaled up, and the handshake messages include different headers. So there should not be possible to confuse a DTLS 1.3 transcript for a TLS 1.3 transcript. It's also not entirely clear what the impact of that would be, even if so. Even if the leaf keys were the same, it won't be possible to substitute packets because the data that is integrity checked is different. So my intuition is we don't need to do anything. I can't actually prove that. I'm curious what people think about how they want to resolve it. I think Martin had some thoughts. Resolving it will be fairly straighthtforward. I can imagine a number of ways. changing the expansion point, changing the initial seed, the initial expansion seed. So if people think we ought to do key separation, it's not going to be expensive to do. But I think when we did it for Quick, there was some sadness from implementers about having to dig that deep into their key schedule, though that may be different with a stack, which is well integrated like DTLS as opposed to Quick TLS.
Yeah, so Martin Thompson, concretely the difference between the two protocols, aside from maybe the choice of extensions and all those sorts of other things, is the message sequence numbers that we have in the handshake messages. And to my knowledge, that's really the only thing that we can rely on being different.
That's correct because the version numbers are not the same.
Right. I'm not especially concerned about that. I do want to. I do think the property is important. I don't want someone establishing a TLS connection on the assumption that they have certain properties out of that and then get DTLS guarantees. I think that would be not particularly great. But I don't see anything concretely preventing us from relying on the message sequence number stuff. It's doesn't seem that important how it's done.
Yeah.
If we are not sure, we could easily use the DTLS instead of the TLS string in the key derivation function. Be done with it.
Yeah, that would probably be the easiest thing. I have to count to make sure we're not going to overflow by one, but I think we have enough room.
My recollection of the space that we had available was that we had good amount of space, though not a lot.
Okay.
It's like 13 or something was the limit from memory.
Okay. Well, so I guess in that, I mean, I'm sort of like, I'm tempted to be conservative unless somebody, I guess the reason we didn't do it in quick was because I think a couple people were sad. So unless someone is actually sad about this, my intuition is to be conservative. So I think what I would suggest is, why don't I go count? And if we have space, we can just do it. And if we don't have space, then we can come back and ask.
We can choose a different string entirely. in that case.
DLS 1 3 or something.
Or just D.
Yeah.
But
Is anybody sad about that? Okay. I'll make that change as soon as the draft. And I'll do whatever counting, though. I think Kazuho and Martin, I'll be asking you to help me count.
All right. So then after that's done, did you have one more comment?
I think we're done.
Yeah. All right. We have 3 interoperable implementation: embed, mint, and NSS. Martin, do you have a comment?
yeah, so I raised a comment on the connection ID draft.
Yes.
That I think also applies to DTLS 1.3. So we should, sorry, that's on the agenda. Okay.
Yeah.
So there is that other technical
Yes.
problem that we have to think about.
Yeah. And once we work through that, assuming no change, we will likely start the working group last call for that again and move forward with it. Right. On that note, do ESNI. All right. So this is just an update on encrypted SNI. There are a couple major changes that went into the latest version. In particular, there was a bug around how we deal with HR and potentially leading to nonsense key reuse. So we fixed that with a temporary patch that basically uses 2 different labels when doing key derivation to avoid deriving the same keys and nonces and using them to encrypt 2 different messages. We improved some text regarding trial decryption for certain cases where you want to omit the record digest from the client hello ESNI extension for various use cases where that might be applicable. We landed the greasy ESNI patch, although David Benjamin raised an issue yesterday indicating that it's not yet finished and not yet perfect, so there's still a little bit more work to be done there. And we also moved the DNS extensions out of the ESNI key structure itself, so the new format is a single structure that has an extensions blob for DNS things, whatever DNS things you want to put in there. That would be the address set that's currently specified, or some other thing that might be specified in a later draft, and then also the ESNI keys blob. Next slide, please. And then there are some minor changes as well, just to kind of clean up some editorial nits and improve readability of the text and so on. So I encourage you, if you're interested, to just check the diffs for these. Next, please. So there are a couple, there are several open issues. The ones on the left are the ones I'm going to try and talk about today. These ones require some discussion and potentially some non-trivial changes to get right. The ones on the right also are open and just require some more engagement from the folks here to sort of come to closure as to what to do. In particular, compressing the server name and the client hello, whether or not that's something we want to do. There's not been much activity on that particular issue. The Greece ESNI extensions was the issue I was referring to earlier from David Benjamin, and then the ESNI include the zone DNS zone apex problem. Patrick had a PR that needs to be updated for that to address it, and potentially we can do that at some point, or we just do the HTTP service record thing. So anyways, next slide, please. Let's start with a problem that is existing in the current draft. So assume you had the following topology where 2 servers in your supposed anomaly set have different cipher suite configurations provided or just enabled for whatever reason. So host A on top supports both AES and Cha-Cha. Host B on the bottom only supports AES. Next slide, please. And then suppose your client sends a client hello in which he prefers AES over Cha-Cha and sends it along, and some on-path adversary intercepts it. Next slide, please. And then swaps the order of the cipher suites such that Cha-Cha is preferred. What he'll get back if he sends this packet to host A as a server hello that has chosen Cha-Cha And if he sends that over to host B, he will get back a server hello that only, a server hello that only supports AS. Therefore, sort of distinguishing what host was used when connecting to this particular, or when opening up this particular connection. And this is possible right now because the only thing that we use, go forward one more slide. Right, because the only thing that we bind to the ESNI key extension is the key share in the client hello and nothing else. And so this simple example kind of illustrates that the cipher suites must also be bound to the ESNI extension, but it's sort of perhaps not the best thing to, the best approach to sort of patch these in a sort of piecemeal fashion. So go add more and more things as we discover they need to be bound. So ideally all non-ESI extensions and contents in the client hello must be bound to the ESNI extension. And then we kind of just solve this problem in one fell swoop. That would prevent probing based on modifying any parameters in the client hello because everything is bound to the ESNI extension. And by virtue of including the key share as part of that set, you prevent the cut and paste attacks that are currently prevented. So I think what needs to be done is to bind more things to the ESNI extension. Next slide, please. But there's also another example. In this case, assume the client hello, same topology setup, server supports, the two hosts support the same cipher suite configurations. This client sends a client hello in which he prefers to child over ES, and the adversary does absolutely nothing. He simply just forwards them to two different hosts and gets a response back. He can then distinguish what the SNI value was based on prior knowledge of what the cipher suite supported cipher suites are for those particular hosts. Next slide, please. There's really nothing we can do about this. If a server anonymity set, or quotes, is configured in this particular way, we can't stop an adversary from doing this sort of probing without modifying any of the client hello contents. So ideally, servers that are in the same anonymity set respond to client hello messages the same way for every non-ESNI piece of the message. Yeah, Eric.
Chris, I'm not sure I'm following this. Can you scroll back one slide? Sorry, so what is the relationship between these two servers? They're different origins?
So different origins?
The different origins?
I'm not assuming any. I'm just assuming that they're supposedly in the same anonymity set.
Right. But why isn't, is this assuming you're not binding in all the, but you're assuming you are binding in all the properties, right?
Yes.
Right, okay.
So the adversary doesn't change anything in the client hello. He just simply forwards them.
But I guess my point is one of them shouldn't be answering, right?
Sorry?
One of them should, one of them, I mean, one of them, only one of them matches the SNI.
Yes.
So why is the other one answering at all?
Yeah, perhaps it's a grease extension, or it's a greased ESNI value, but I guess in that case, yeah, perhaps you're right.
Want to go to fallback? If they're purportedly in the same anonymity set, do you get the fallback?
Yes.
I mean, there's a basic problem that I think that I mean, that certainly is correct, which is that, but I mean, so I think David and Benjamin and I were talking about this last night. I'm not sure if I see him here, but that, you know, it's certainly the case that just by watching how the server responds, you can learn whether it's A or B, because you learn whether it chooses GCM or Poly 1305. So like, Poly. So I mean, like, as a practical matter, they have to, for these cipher suite attacks, they have to behave identically, or you're just like, I mean, like, probing aside, observationally, if I have the connection go through, I can click on which one it chooses.
Right.
So I think like, observationally, we have to behave identically in this case.
Yeah. Yeah. Thank you. So yeah, and to Martin's point, you should fall back. So perhaps this is not the correct example, but the underlying point is the same. Yes.
Yeah. Martin Thompson, can you go forward a slide, please? Oh, no. It was the anonymity set partitioning slide that had the potential solution here. I think what you really want to say here is that servers must produce similar choices for its server hello extensions and server hello, rather than having completely identical responses across everything. Because once we're past the server hello, everything's encrypted. So if you have an extension that's responded to in encrypted extensions, you are allowed to make different choices at that point. It's your, I guess, your cryptographic configuration that needs to be consistent across all of those things in the same.
Yeah, I think that's more crisp and correct. Yeah.
Yeah.
Thank you. Yeah, Rich.
Yeah, Rich Solakmai. Yeah, yes, to what Martin said. I had assumed that it was always that was sort of implied by the doc.
It's
Therefore-
not currently stated, so
I
we
know.
should probably explicitly state
Yes, yeah, make it explicit and point out the dangers of what happens if you don't do it.
that. Martin, could you open an issue perhaps for that? That would be great. Right. So moving on. So this is the more interesting attack that came up in discussions with Eric and David and Stephen. And it basically works like so. And this is assuming the current draft. Client sends a client hello with ESNI, valid ESNI, non-egregious extension to a particular host, who sends back an HRR. The on-path adversary then, by virtue of responding to an HRR, swaps in its own key share, swaps in its own ESNI encryption of encrypted SNI value of whatever, and then sends it to complete the connection to the server. If the server doesn't check that the SNI value that's in the second client hello matches that of the first, or rather checks that the inner contents of the ESNI extension match that of the first client hello, perhaps because he's made a determination based on what SNI to use from the first client hello, then the server will happily complete the connection, sending the certificate and corresponding SNI value, which is selected based off the SNI value from the first client hello. So the adversary can just finish the handshake and look at the certificate to figure out exactly what SNI or probable SNI was used to complete the connection. This is not great. So moving forward. So ideally what we want is we want to require the servers to do this check. And we can say in text, the servers must absolutely check that the contents of the first ESNI extension match that of the second, otherwise fall back to the public name or do something. But this is not really a cryptographic check in any particular way. And it's also prone to implementation mistakes or servers, people implementing servers just choosing to, skip over that part of the text, in which case a client is still kind of in a bad position. So ideally this would be achieved somewhat cryptographically. And the proposal, actually, if you just go forward, the proposal is to, or a proposal rather, I'm open to suggestions as we're all open to suggestions, to include something from the ESNI extension in the key schedule. That has the effect of effectively binding that ESNI extension from the first client hello to the duration for the rest of the handshake effectively. And I realize that people may react negatively to putting things in the key schedule, but I think of all the options, that gives us the guarantees that we want in a pretty intuitive way. So, I mean, of course, subject to formal analysis from our friends. Yeah, Martin.
So, Martin Thompson, to be clear here, this is us making it impossible to do the wrong thing, rather
Yes.
than simply leaving that up to implementations and at servers to do that on their own discretion. And there's a number of ways in which people might take information from the first client hello and try to save effort in processing the second one. And because this is a pretty significant cost in terms of processing, I can see how that might be the case.
Yeah.
Particularly when you're talking about using the ESNI extension to route on that first client hello. So you kind of need it on the first one. There's a strong temptation there.
Yeah, exactly.
I don't have a strong opinion on what we do here, but changes to the key schedule are awkward, but doable.
Yeah, awkward for a number of reasons. Like, in which direction does it go into the key schedule? How do you, does it come in as a PSK? But what do you do then if you're resuming a session that has a PSK, or put it in the ECDH key share? And what if you want to do another thing that happens to modify the key schedule, which will be discussed later?
Yeah, so the post-quantum hybrid stuff,
Yeah.
the draft that Douglas has is actually really good sort of formulation of how we sort of think about these sorts of problems. And I sort of wonder whether we need to think about this more concretely in the abstract a little bit before we start tackling these sorts of things. Yeah.
Absolutely. Yeah, thank you. Becker.
Yeah, I mean, it seems like we should probably separate out two questions. One, what is the general strategy which to follow here? And the second is, what are the specific mechanics of how it's done? In particular, as Martin suggests, if we're getting to the point where we think we're going to do a lot of key schedule additions, then it's probably worth cooking up some mechanism for doing that generally that allows arbitrary insertions at each point. I'm not going to say I regret not allowing that before. Life was complicated enough, but probably a problem to solve now. The thing I'd like to understand that I don't think I understand yet is what the sufficiency set is for things that are going to solve this problem. Namely, the sufficiency set. Namely, is it enough to just have something in the key schedule? Do we also have to do a binding across the client hello? I think we're getting complicated enough now that we're going to need some formal analysis to reason about it. We had some initial puts on this, but so it seems like the next step, probably rather than discussing exactly what to do here, is to sort of leave this as an open question and for input, and then and then have a small group of people go off and like interface with Karthik Bhargavan and Kaz and like have them help us work through the problems. I think getting new ideas is like fantastic, and because a new idea is great, but trying to decide which one is to do now seems like not very practical. I don't think we have information for that.
Yeah, I mean, we could even form like a design team of sorts to go off and focus on this particular problem. The current thinking now is to do both the binding and the key schedule searching, because it seems like to be the most conservative, and kind of intuitively you want to include everything in the client hello into the ESNI extension. But of course, subject to change based on analysis and outcome from discussions with our friends. So I don't know which of you was first.
I believe it was me.
Yes, please.
Jonathan Hoyland, Cloudflare. So I'm currently trying to write a draft on how to inject stuff into the TLS key schedule without breaking all the formal proofs with Chris. So that is definitely something that we should probably do. But just as a question on this, could you comment on why this can't be done in exactly the same style as the PSK binder? So you just include the same stuff as the PSK binders would have included?
You mean have the ESNI extension be the penultimate extension in the client hello just before the PSK binder?
Well, I wouldn't define it like that. I would just say the truncate client hello doesn't include things that say they aren't included, and all of the ones that aren't included must go at the end, because you can't do cyclic hashing. So yeah.
That is one of the options, yes. I guess a issue with that is that if we have to do this again for whatever reason, then are we going to start just stacking up extensions on the bottom of the client hello? What about the ordering for these things? And it becomes tricky. And there are other proposals as well to do the binding. I'm not proposing a specific solution right now. I'm just saying that perhaps we should do that. We should do the full binding.
Yeah. But yeah, this is one of the reasons why I'm trying to define the layering thing.
Christian Wiedemer. Yeah, I mean, when I see this business of incorporating all ESNI, all client Hello extension in the ESNI, I just went through the motions of updating Kazuo's code from the draft 02 to the draft 03. And there are some code paths that become really, really shitty if you have to go to all the extensions, because effectively you get a variation of who's on top. And if we have to solve the who's on top of like, oh, I'm the SNI extension, I'm on top. But no, I'm the PSK extension, I'm on top. Oh, that kind of stuff is not healthy.
Yes, I would agree.
So I would very much like to say that whatever secret we treat, we inject that secret somehow to make a binding, but we don't require all this chaining of extension and interdependencies, because it makes the code very fragile.
To be clear, are you suggesting that we don't need to bind to things like the cipher suites beyond the key share?
I don't know that we need to bind none of them or just one of them, but I would say that a requirement to bind all of them results in code that is terrible to maintain.
Sure. This proposal is trying to take the conservative approach where we might, say we minted this RC and the only thing we included was the key share in the service suites, and we discover, oh shoot, there's this other parameter that could possibly be unbounded and used to break ESNI. It'd be best if we could avoid that situation, and doing everything does to avoid it.
Basically, I like the fact that, if we somehow inject the result of the secret into the handshake key, then we are guaranteed that an attacker will not decrypt the handshake, the encrypted handshake. And then we are only concerned with what leaks in the clear text server hello. And that becomes a much more tractable solution.
Not quite fine, but perhaps we can talk offline.
Okay.
I think Ecker, you were next.
Yeah, I think so too. Yeah, I think the message here is clear. We've gone through a couple of cycles of this, and clearly we don't have the tools yet to reason about it. So I think what I'm interested in doing, as I indicated earlier, is getting the tools to reason about it. So I'm perfectly happy to have a belt and suspenders approach in which we have several things, and that may in fact be valuable for other reasons, as we've discussed. But what I'd like to understand is what every individual component we're adding is doing and which attacks it's stopping, so that we have a complete model of the attack picture. Because it seems like what happened here, I'm not naming anybody because I was involved with this as anybody else, but what happened here is we had a partial attack model, and so we closed the attacks we knew about, but then we didn't have a way of reasoning about all possible attacks. So I'd like to get to the point where we can reason all possible attacks so that we know we're doing the right thing. And then if we need belt and suspenders, then fine, or if we determine the belt and suspenders is good, also fine. But I just want to make sure I understand what everything is doing and how they hold together.
Yeah, correct. Thank you. Jonathan?
Yeah, there is some research on exactly what you would need to include in these scenarios by Kartik, so we should ask him.
Oh, absolutely. He's on our list. 10 minutes. Okay. All right. Let's move to the next issue. I actually quickly go back. I'm sorry. So the issues that I just described led to these three questions. The first of which I think is we have a very clear answer for. Do we require that servers are in the same anonymity set sort of behave identically? Yes. I think unless anyone objects to that, speak now for everyone piece. So we discussed the binding issue. So perhaps continue that in the smaller team or on the list or whatever. And then relatedly, we'll work on how we do the binding of the first and second client hello in the HRR case. Yeah, Kyle.
Kyle Eckritz. I think if we make the number one an absolute requirement, that in the most sense prevents any changes in a distributed system at all. So I think we should make sure we know the implications of exactly that, absolute requirement.
Yeah, so by require, I don't mean put a must in there, servers must do this, but they should do this, and if they don't, here's what can happen.
Nick Sullivan, Cloudflare. I think, question number one does complicate the deployment pretty significantly, and I would not be in favor of requiring that. It's different even if you're using a single proxy. Various websites or domains will have different configurations for different reasons, and forcing them to conform to the same cipher suite set is not necessarily going to work. I would like the anonymity set to encompass as many domains as possible, rather than singling out the ones that have special requirements.
Yeah, I suspect this is mostly just a text editorial issue. I think we're in agreement that, yes, ideally, servers that have similar configurations there's many servers in the same anonymity set that have this particular configuration, not all the servers that are under control of a particular operator shaped exactly the same way. But yeah, Subodh.
Subodh Iyengar. Irrespective of ESNI, it seems kind of undesirable to have the entity generating the HRR client hello be able to be different from the entity generating the original client hello in the first place in TLS. Maybe it's a more general problem than just ESNI fix it for TLS itself, where we can guarantee that the entity generating the new client hello during the HRR is the same as the entity that generated the original client hello in the first place.
Sorry, are you asking, are you saying we need a mechanism to be able to prove that the client who sends the second client hello is the one that sent the first one?
Yeah, I mean, like, there's nothing specific to ESNI here.
Right.
It's just that ESNI exposes this thing to, like, we don't get the privacy properties out of this because there's a, I wouldn't say a flaw, but unanalyzed case in TLS in such a way. And so we expected to get these privacy properties, but we didn't get these privacy properties. Can we fix TLS 1.3 to such that we'll get these privacy properties back from the TLS protocol itself? We don't need these hacks for ESNI, but it'll just work generally for any other extension that we add in the future.
Yeah, very good point.
I think I'm next. So on this question 1, certainly it's possible to not require that all servers in the same anonymity set behave identically, but this was the point of the comment I was making earlier, that definitely does leak information. Because the way to think about this is, imagine that you have an anonymity set of K servers, and K-1 servers all prefer AES GCM, and the K server and the remaining server prefers Cha-Cha Poly. So all I have to do is watch the transactions. And if the transaction comes through and it's Cha-Cha Poly, I know it must be that K-1 server. And so that's not a probing attack, that's just an observational attack. And so as David Benjamin pointed out, that's not as good as a probing attack, but it's certainly a plausible attack. And so to the extent to which servers don't have the anonymity set identically, they're partitioning the anonymity set in some ways, and there's not really much to do about that. And we're just going to live with that, I think. And the advice ought to be, do the best you can, have uniform configuration, and ESNI is not going to be a perfect defense. It's a partial defense, but the advice is that we'll just partition the anonymity set in those other circumstances.
Thank you. Martin, can you?
Martin Thompson was going to say the same thing, so that's one.
Thank you.
Ben Kadek, I had been thinking similar things to what Subodh was thinking about. Is this a more general question? And I think we did briefly consider this when we were writing TLS 1.3, and we concluded that we didn't want to make the server have to do the work all the time to keep the state, because it didn't matter that much. And it may just be that the conclusion here is, if you're going to do ESNI as the server, you have to do more work.
Seems reasonable.
Rich Stahl-Akamai, just on the server side, to echo what the browser side said, yeah, if they're not looking the same, then you can partition them operationally, so don't do that.
Yep, don't shoot yourself in the foot.
Eric Nagonakamai, and +1 to what Nick was saying, if we, especially in question 1, if we can provide guidance, but if we start trying to enforce things too much, it'll just require lots of it may mean that people operationally just start splitting things down and defeat the purpose.
Cool, thank you.
Kyle Micritz. As far as the question of this being a more generic problem, I think one thing that's special about this is that we do have the potential to use some kind of a shared secret with the client key share, whereas most extensions we do not have that, and usually we're sending a HRR in response to not having an acceptable key share in the first place. So I think this would be a bit more difficult problem to solve generically.
Yeah, good point. Thank you. Can you move to the next slide? Right. So we'll continue that discussion on the issues and on the list. The next big one is HPKE and whether or not ESNI should adopt it. So for those of you who are not familiar, HPKE is hybrid public key encryption, basically ECIS, but with chems and dems. The contract for HPKE is that you generate, whenever you encrypt to a public key, you generate a new fresh key share effectively for each encryption. And there's a cipher suite that says exactly what algorithm you use for doing that encryption algorithm. In ESNI currently, we basically do ECIS with Diffie-Hellman, and we reuse the key share currently, meaning that upon getting an HRR, you would send the same client ESNI key share that you sent in the first one. And the cipher suite used to negotiate which particular algorithms for ECIS is sent sent in the ESNI key share using the TLS cipher suite spec. Forward. So the benefits of HPE adoption here are that we don't roll our own crypto, and we use something that the CFRG sort of blessed in a way. The drawbacks beyond it being an active draft currently and still under construction and still in need of analysis are that by changing the ESNI key share effectively on HRR, you are forcing the server to do another public key operation. In processing that might be a deal breaker. I'm not sure. So, I mean, there may be other benefits and drawbacks as well. Perhaps, Martin, you want to raise one?
Yeah, Martin Thompson, the size of the packet's starting to get pretty big. And so if you have to put two separate key shares in, you've expanded the usage space. And we have primitives, but the flip side of that is that we have primitives that reuse of the key share doesn't work for. And so we need to be aware of that. So we were looking at SIDH, for instance, and you can't reuse a key share in that context.
Sorry, the ESNI key share is already separate from the client hello key share used with Handshake.
Oh, right, sorry.
But yes, there's also the issue you're mentioning about, right? If we were to go back, there would be that issue. Yeah, David Benjamin.
David Benjamin. I think it might make sense to look at this after we've sorted out all the like binding stuff, because that might change the things we want out of our crypto box thingy. For instance, I don't know if HPK lets us derive some like random extra key to stick in the key schedule. And so if we decide we want to do that, then this might constrain us. So I would suggest we like make this decision last.
Very good point.
I agree with David's position with a slight friendly amendment, which is let's sort out what we need. And if it's close enough to HP key, but not exactly HP key, let's call CFRG and tell them to change it.
I think Richard is in the room, hopefully, and I'm sure he'd be willing to change it.
So in for instance, we wanted, I don't know what you would call it, but HP key plus ancillary random output, like that seems like pretty easy to generate. So presumably, like the purpose of the work in CFRG is partly to support the work here. So.
All right. Yeah, that's certainly an approach as well. We have one more issue. We have one more important issue. Hopefully we can get through this really quickly. And that is of split mode. Currently the drafts supports both shared and split mode. In the split mode case, basically the client-facing server has to send some secret key material to the backend server. Right now we suggest basically doing that by sending it prepended to the client hello on the TCP connection, encrypted under a symmetric key that the two endpoints happen to share. And you might want this for some use cases. Next slide, please. Next slide. Benefits, there may be use cases that require this. Drawbacks, of course, that this does add complexity to the document. And it, depending on one's perspective, it might constrain the things that we could possibly encrypt. You might imagine in share mode, and ESNI with only shared mode, you could potentially encrypt more than just the SNI, like ALPN, et cetera. It's also potentially part of a more general protocol that Ben will be talking about in a little bit. So I posed the question to the group, should we include it, to what extent, or drop it?
Eric Squirrel again. The document doesn't really include it or not include it. It just says this is consistent with its operational mode, and then it has some hand waving about how you'd implement it. So I'm not quite clear on what complexity is being added here. If we get to the point where including it, where having a document which is compatible, like I see it as a requirement rather than as a function in this protocol, they need to be requirement to be compatible with the split mode. If it turns out that requirement is like causing us a lot of pain, we can revisit it. But until then, I'd like to have the requirement continue written down so that we remember it, because I think it is an important use case. Yeah, maybe we can't get them all, but like let's not like shorten our sights until we know we have to.
Would you just quickly, assuming like the proposal that Ben came up with was fine, would you be okay like referencing that instead of describing sort of the thing we have currently?
Well, I mean, if you mean the thing we have currently, you mean the ridiculous hand waving at the bottom about how to like send Z?
Yes.
Yeah, totally.
Okay.
That part is fine. But I think that it's important to have the prefatory material that says like it's supposed to work this way so that people remember how this is supposed to function, so that as we work on the document, then we don't screw it up.
Great. Okay. DKG.
Yeah, this is Daniel Kahn-Gilmore. So I definitely think this is an important requirement for this case. There are going to be people who want to operate a protected server in the backend that can't share the content with the front-end server. So yes, please make sure that this stays as a requirement.
Great. Stephen?
Yeah, agreeing with Ecker and DKG. Also, there might be more than one way of doing the back end of the split mode in future. So I think we keep the requirement. I'm not sure we want to normatively say, here's the one true way of doing it in this document.
That's fine with me, yeah. So we can update the text accordingly, just maintaining the requirement and then describing potentially one might go about doing this. And I don't think we have any time for the rest of it. So please take a look at the issues. They're on the GitHub page or on the GitHub repo. Comment. I will try to summarize what are the big open questions and send them to the list, encouraging people to comment. And regarding the earlier, more non-trivial changes, I guess if anyone's interested in working on this particular problem, we can get together with our formal analysis friends and kind of back to it. So Christian raised his hand, and I'm sure the other people who we've been talking about will be interested as well. So I think that's it, unless there are any other questions. Great, thanks.
Connection ID.
It doesn't work.
I try to be brief. So the connection ID topic, so there are at the moment 3 documents I would like to talk about. The first 2 on the top are the connection ID for the DTLS 1.2, the connection ID for the 1.3, which is in the DTLS 1.3 specification itself. And then there's a new document on the bottom, and I will get to that in a minute. Next slide. So this is the regular behavior. So if you remember, and I'm not going to repeat the use of the connection ID again, but we had regular client IoT device talking to a server via NAT, and the NAT obviously changes the IP address, source IP address, and the port as well, typically. And so you have the connection ID in the payload, which associates or links to the keys and the algorithms. So everything good so far. The NAT makes these modifications, and that's exactly the intended behavior. Next slide. Unfortunately, late in the process, we found out that we missed an important security consideration. It's really a shame, actually, because some of us worked on this in the mobility space beforehand, so we should have actually noticed it, but blanked out on that. So here's the case. Imagine that there's an on-path adversary who is kind of like a NAT, but is able, obviously, to change the source port of the packets that pass through. And so he changes it to redirect the traffic to some remote server. And in case there is an asymmetry between the traffic that goes from, in this case, the client to then finally the victim, then this adversary is able to make an amplification attack. That's obviously a problem. What I didn't describe in the slide is the case where there's an off-path adversary who injects some packets, but thanks to obviously the properties of DTLS with authenticated packets, that's not possible because the attacker can't mint the packets with the correct key to make them pass through the security checks. And so you wouldn't update the binding in your database to send the return traffic to this newly indicated IP address without actually checking the cryptographic parts of the packet. Martin?
So just a small amendment here. The adversary does not necessarily need to be directly on path. There can be an observer that is able to receive the packets. Yeah.
Right. Going to the next slide. Yeah, actually, this is this case. So we'll talk about this one that you just raised, Martin. You see the slight shift of the box in my great drawing skills. So as Martin said, the attacker doesn't need to be on path. So he sees traffic flowing by, but he can't modify it. But what it does here is what this color coding is supposed to indicate. he basically, after the packets from the client to the server pass through, the adversary replays a packet but changes the source and an IP address and port. And as a consequence, if the server doesn't check for that replay, he would send the traffic to, again, to the victim.
So the other observation here is that routing on the internet is not always ideal, and so you might end up in a situation where the adversary has a faster path, and they can copy a packet and replay it, and beat the real packet to the server. It's a race condition thing, but you're also able to mount the same attack without relying on the anti-replay properties that the server might be implementing.
Yeah. So in some sense, you don't necessarily need to enable the anti-replay protection which DTLS offers. You could rely on a newly defined rule which we haven't added to the document yet. It's in a GitHub repository as text, but needs some discussion on that the server needs to, before sending it to this new IP address, he would actually have to check whether this is indeed the newer packet in terms of the sequence number and so on, even if the replay protection is disabled. That would be one possibility to deal with this case.
So that would only deal with the case where an old packet was copied. It
Right.
wouldn't deal with the case where a live packet was raced to the server.
True. If you go back to one slide, of course, there's also the possibility not to basically black hole traffic, which is sort of what this figure is supposed to indicate. Needless to say that if there's an adversary along the path, he can as well just drop packets without having to reroute them unnecessarily. That's also a possibility. So what I'm trying to get to here is that we have updated the DTLS 1.2 connection ID draft with some text to describe those threats, and also the DTLS 1.3 specification to include the discussion of those. And that's, if you go back to the second slide, there is a new document out there that provides a DTLS-based return routability check, which is this document at the bottom. There is, of course, also the possibility to expose these address changes up to the application layer protocol via the TLS or DTLS-specific API and let the application deal with it. That's possible as well. In some cases, depending on what type of application traffic you have, these issues that I just talked about may not be as severe as they look like because, for example, in co-op, you typically don't have, or you don't have this one message to the server and then a huge amount of messages going back because of the stop and wait nature of the protocol. It has a congestion window of 1. So that's not there. But in a generic case, one could imagine that DTLS is also used to secure traffic where you have a high asymmetry, and then making use of those return routability checks specifically provided at the DTLS layer makes a lot of sense.
Yeah, so Martin Thompson, the other thing to observe here is, and I've got to credit Eric here, who's sitting over there. Eric Kinnear has done a lot of analysis on this thing for Quick, and there are a couple of other cases that you might want to consider in your threat model, depending on the decision you make. There's a good write-up now. It's in a pull request on the Quick specification. I can send a link to that to the mailing list. The return routability check that you described does not necessarily cover all of these cases adequately, unfortunately. And so there's logic that you need to apply in both endpoints, in fact, in order to make sure that you're not subject to attack. So I would encourage you to read what we've done in Quick and read Eric's analysis of that. And I would suggest that you copy that design. Let's not do this twice.
Yeah, we obviously looked at the Quick text, and that's a good idea. And that's also why we decided to have a separate document on this, because it can advance independently of the other stuff for those cases where that type of concern is big enough to warrant a return routability check procedure. And I think it makes sense to have something at the DTLS layer, very much like you guys did in Quick.
Eric Criscuola. So I think there's two questions here, one of technology and one of, perhaps three, one of layering and one of document structure. So when we decided to add the connection ID to DTLS 1.3, the general concept was that we're going to add the machinery that you would need to do the connection ID because those had to live at the transport layer. But then any of the machinery you needed to handle the changes in connection, changes in IP address, we put somewhere else. And I think that this existence of this RRC document is a good example of why that's a good design decision, because it means that we can worry about the migration case while continuing to let the base protocol advance. And this is the same decision roughly made for DTLS 1.2. So what I think here's what I propose we do, both for technical reasons and also for expedience reasons. I propose that we say in the two drafts up top of this, the CID draft, the 1.3 draft, here's the machinery for connection ID, and DTLS shouldn't automatically do any kind of response to this. It should just accept the packets as it is and should not adjust the peer address. And then it should say, here are some considerations about what you would generally need to do in order to adjust the peer address, but it's the responsibility of the application or some future extension like the RRC draft to tell you how to actually do that. And that lets us advance the wire format mechanics for people who need them, and then co-refine the return reliability check with Quick and get the right answer. So that's how I propose we actually get it.
Does that mean PR7
I would, yes.
Sorry, my question was whether that meant that the PR number 70 on the CID draft goes away.
We'll have to refine it a little bit, but I think no. I think it needs to duplicate the text that's in one. Well, we need to take the text in 1.3 and the PR number 70, harmonize them, and then lay them in both places. And they're roughly correct, but I think that the thing that is in 70 that is not in the 1.31 is a little bit of discussion about the general kinds of conditions under which it would be safe to, maybe do a fast response, and also a prohibition on a clear prohibition on the DTLS stack doing it itself.
Yeah, it would be nice if we have the same text in 1.3 and 1.2. Currently, there's different text in those two documents. I think it would be nice to harmonize it.
So you two are going to work on that on a plane somewhere?
We book some separate flights for this.
You're on the trail. You guys are going to run for a long time, and you can talk it out. It'll be great.
Eric Kinnear, Apple. So one, hi, and we should definitely talk. That would be great. Looking at some of the attacks, I think one of the pieces that is most interesting here is how you handle when you notice that you're receiving duplicate packets that potentially share a connection ID or not, where some adversary in the middle that's observing your packets is racing them. Because I think that's one of our only identified paths towards kind of being a little bit more resilient to that kind of attack. And it seems like there's a little bit better chance to harness some of that here than there is in Quick. So I'd be interested in chatting more about that offline and seeing if we can kind of merge some of those things together.
Hey, Martin, let's keep it quick.
Yeah, Martin Thompson, I think you want to move all of the migration pieces into this RRC draft and actually talk about that as a migration document based on Neka's suggestion.
Wonderful. We have our marching orders. Thanks.
Cool. Thanks.
All right, compact TLS.
So this is by way of an informational presentation more than anything else, and information two ways, I suppose, to tell you about it and get people's feedback. The context here is, well, that there's been increased interest in having an AIC which has smaller messages, or is generally smaller. This is initially prompted by some of the work in Lake for the need for IoT to have compact key exchange. I'm gonna take this off. Next. So, so the question is like, you want a compact key exchange, like what do you do? So we spent like an enormous amount of time on 1.3 getting it right, or at least as right as we know how to get. It's got an extremely widely studied. We have all these papers. We have like a lot of implementations. It's already a pretty large fraction of traffic from browsers, and we're seeing increased deployment in other places as well. It's like a fully general protocol, or at least maybe too general, and we're already seeing a lot of extension points, like you're seeing subcerts and maybe it's RRC staying in ESNI. But like what it really is not super compact. The original design wasn't that compact, and we didn't like really make much effort to make it more compact. There are a few places where we try to shrink things down, but generally this was not a design goal, in large part because so many of the applications of TLS involve certificates, and the certificates are so large that basically they dominate the size of the packets. Next slide. But it's turning out that there are other applications where people like to have a much smaller, much more transcript. First of all, well, not transcript actually, I should say, a much more wire image. This is, I say, initially prompted by some work on IoT, but also we separately had conversations in Quick about how big like the Quick messages are and how nice it would be if we could get them a little smaller, especially in the client hello, where we're narrowly restrained to the first 1,200 bytes. Unless you want to have some sort of extra machinery, as David Benjamin has pointed out. So there are two general approaches to fixing this or addressing this. One is to keep the protocol general, but just like try to cut out all the gratuitous encoding overhead. So TLS is full of gratuitous encoding overhead. A very common idiom will be to have some data block which has length defined, and then have it be a vector of things which has the length in front of that. And so now you have the length of the thing and you have the length of the vector, and like those are completely duplicative, but they're still there. And it's especially, this is actually a real source of engineering defects, by the way, where you'll like write, you'll forget the external length, you have like the external length field and you forget the internal length field, and you have interrupt problems. I've made this mistake a number of times. I'm sure other people have as well. So you can remove all the redundant length fields. There's also lots of places where we have like fixed length fields for things which are almost never as big as they ostensibly are supposed to be. So a really common pattern will be like handshake messages can be up to 2 to 24 bytes long. I don't think I've ever seen a 2 to 24 byte handshake message unless someone deliberately made it that long by like adding a bazillion certificates. So I think Barnes and I pathologically made one day on the plane, but generally this doesn't happen. But nevertheless, you're always consuming 3 bytes for the length of the handshake message all the time. So this is a gratuitous, and again, this wasn't a big deal when we did 1.3 because there's plenty of room. But if you want things to be small, it's gratuitous. And so we have variable. It's possible to replace those with variable length integers, and things get smaller. There's also a number of places where you have values which you could say were explicit or were explicit where they might be implicit. So a good example here is that if you only support one elliptic curve type, then why are you bothering to say, here are the curve types to support and here are the key shares that go with it? So you can imagine saying, look, I just gave you the key shares and I'm not going to take any others, so don't bother bothering me with an HRR. There's also some places where it looks like there's some excessively long crypto variables. The random is a good example. It's not really clear we need a 32 octet random. Now, of course, we are like chewing up a bunch of, we're increasingly using up that space for various kinds of sentinel values, so it's not clear how much room we actually have left, but it does seem like these limit some. There's also some questions about whether or not we can make finish shorter, because finish is quite long. So this is effectively just like TLS 1.3 with a better encoding. And so you basically get an isomorphism between 1.3 and CTLS, and it's pretty easy to convince yourself that they're the same protocol. And if you look at all the analysis work in the proofs, all analysis work was basically done without really looking at the wire encoding in detail anyway, and so certainly doesn't pay much attention to, for instance, how long the length fields are. So that's like strategy 1. Strategy 2, which was suggested by Karthik Bhargavan, is to sort of go the other direction and say, let us like remove generality and instead basically have a compression layer that takes sort of your fully general TLS protocol and then compresses into a reduced version that goes in the wire. And so you probably want some kind of explicit or implicit shape parameter that told you what that compression was supposed to look like. And then what you end up with is a very small wire transcript. But what you probably want to do is then re-decompress that into like a full TLS transcript that you feed in everything. And so you think of it as basically a compression layer between those two. This is, I think, has a nice property. Yes.
Hi, I'm a native English speaker, but I'm struggling to follow you at your pace. Would you mind slowing down your speech a little? No.
Sure.
Please, thank you.
Right. Would people like me to restart this slide, or should I just continue? So as I say, you probably would want to take the transcript and then re-expand it back into the full TLS transcript. So basically you have this TLS 1.3 for all the key schedule, et cetera. This also has the advantage that then all the things that you were essentially compressing down get rematerialized back into the transcript, so you know the negotiation is correct. This may or may not require some kind of cross-protocol defense to avoid having CTLS talk to TLS 1.3. You can think of that as a feature or a bug depending on your perspective, so that's why I say you may or may not want that. Either approach has like the reasonable chance of keeping the existing proofs valid, which is the main thing we're trying to do. The main theme here, right, is we have a protocol which is spending enormous time, we spend a lot of time engineering, and we spend a lot more time engineering adding things to, and we'd like to continue getting value out of that while still having a compact protocol, rather than having to have a separate line of compact protocols that then have to incrementally be extended in all the same ways that we're extending TLS. To give you a concrete example of this, I was AD back when we did the conversion, we did kernel, and so we had this process of having to like incrementally add curve 25519 everywhere across the IETF stack. And it was just this giant effort of like crossing out like P256 and writing 25519. And so not having to do that would be very nice if we wanted to say add post-quantum. Next slide. So here's like a concrete example that just shows how much like redundancy we've managed to create. Here's like the client hello, the straight up TLS 1.3 client hello. So the first field is the protocol version, which now we've abandoned because we negotiated supported versions. The second field is the random value, which is, as I said, 32 octets long. The third field is the session ID, which, by the way, we've abandoned because we do PSK. The fourth field is cipher suites. You'll notice that has a 2-byte length field and can allow you to have 65,000 bytes worth of cipher suites. Now, we haven't defined 32,000 cipher suites, and I can't imagine any sensible person wanting to advertise that many. So there seems to be a fair amount of extra slack here that you don't need. Then we have compression methods. Have I mentioned we removed compression? And then finally we have extensions. And again, the extensions can be up to 65 kilobytes long, which like is pretty long, and there are like lots of reasons to believe you might only need like a couple hundred bytes of extensions. Typical client hellos range in their sort of 200 to 300 byte range for this area. Christian.
Looking at your example, I am a bit puzzled that you think of restoring the transcript, because if you remove the legacy session ID, which is effectively a random number, I mean, your transcript is going to be somewhat affected, right?
Yes. So this you'd have to not do legacy mode for this. But remember that unless you're doing compat mode, that's an empty string anyway.
One advantage of reconstructing the entire original TLS 3.3 is that makes it the existing proofs trivially applicable, because you could act like you're actually sending the full thing, even though you're sending much smaller.
Yep, that's the intuition that Karthik gave us. So next slide. So this is what you can do if you're like trying a little bit, and really only a little bit. So you say, well, look, the protocol version will cut it down to 1 byte because we don't have a zillion versions. The random will shrink by half because we don't really need 32 bytes. Again, we don't need a lot of cipher suites, we'll make them 1 byte long. Then we remove all the things that we didn't need. The version of string becomes shorter. And then we take cipher suites and we have a variant length encoding for the length, and so you don't need to burn up to us extra octet on the length. And oh, by the way, can you just go back one slide? I forgot to mention, the extensions field, you'll notice, has its own length field that attaches to how long the vector is, even though the extensions takes up the entire remainder of the message. It's like simple subtraction will tell you how long the extensions field is. So once again, you have extra slack. Next. So hence you say basically the extensions field now is the remainder of the message. So if you take this treatment and you like apply it to TLS as a whole, you get actually a pretty substantial amount of reduction in message size. So this is like strategy 1. Strategy 2, next slide. If you're willing to like really go crazy and like have like, here is like a, like a, say 3 or 4 octet profile that describes exactly all the cryptographic parameters, you can do really well. And you can have like the initial byte contain only the crypto variables, which is to say the random and the Diffie-Hellman key. that 0 is like, I don't know what we're doing at 0. Like, I'm not aware of any circumstances in which 0 would be an acceptable value for a Diffie-Hellman key. But in any case, so you can really shrink things down if you try hard. Next slide. So I regret that I didn't have like the original versions, but you just have to trust me that these numbers here are like much smaller than the number you started with. So you can do a pretty good job. Next slide. So this is like preliminary work, hence informational. There are other obvious places to do optimization. We're working with Karthik Bhargavans and other people to like basically be able to see what we have to do to make sure we have enough isomorphism the proofs actually carry over, because that's the whole point of the exercise. I see Jonathan will have some thoughts on that. We're still trying to decide whether we want to follow the compression strategy, which seems like more compact. And also, do we want to expand the transcript? Though I think the conversations I've had this week are making me lean very much towards transcript re-expansion. Adam.
Adam Mangley. So you presented your two options, but they're not mutually exclusive, right? You're going to be doing both.
Yes.
Yes.
In fact, one of the things you might do with the transcript compression is do those reductions.
Yes. So you cool. The numbers you had on the benefits seem kind of small, right? Is this worthwhile? Like what is the motive for like stripping off a few 10s or 20 bytes?
Basic. So primarily these IoT use cases where basically they're incredibly small packet sizes, and they're trying to get within like they're trying to get inside of like 3 packets instead of like 5 or 6, because these credit stop and wait protocols.
But on the previous slide, I mean, the benefits are 10 bytes. Oh.
No, sorry. This is not a good slide because it doesn't show you where I started.
Ah. Okay.
So a typical TLS client hello is more like more like 150 bytes kind of thing.
Okay. So yes, thank you.
Sorry. Yes, thank you for pointing that out. Yeah, for 10 bytes I wouldn't do it either.
Ben Schwartz. I just would like to suggest benchmarking this against plain old compression, like maybe broadly with a tuned static dictionary.
That's a good suggestion. Thank you.
And also, you might even want to consider putting that on top of this. You could do both.
I'm lost. I think it's about.
And just a clarification question. In your example, you said client hello, but are you applying the same technique to DLS ciphertext records and things like that?
Yeah, the draft has a whole thing for all these things. Yeah. There's still plenty of places to turn the crank, but yeah.
Roberto Payon. I expect this might be redundant, but just to make absolutely sure. The intention here is to show isomorphism, as you say in the slide, right? And then to provide whatever arbitrary transformations during that demonstration. So you could, for instance, apologies, you could, for instance, use a single byte and have a bit in the byte to say the presence of any of these fields and then interpret it. You could do protobus, whatever. That is the intent, correct?
Yes.
Okay, awesome.
Yeah, I mean, the ultimate objective is that you should be able to take any new extension to TLS and it's just convert directly over so that you get it for free when you want to do in this compact mode. That's the ultimate objective.
So Ben Kadek, I saw in Jabber, but I didn't bring my laptop up just to check. This is still assuming like in order reliable transport.
I'm sorry, Ben, I just can't hear you at all.
This is still assuming in order reliable transport. At least
Yes. Yeah. Though you would, of course, like you could obviously have a CD TLS as well.
Right. Yeah, that was what I figured. But
yeah, there's actually the vast majority of the overhead of the TLS handshake, of course, is in the TLS handshake itself and not in the DTLS extensions. But those are also fairly bloated, and so there's places to remove things as well.
Yeah, and just a different point with my own hat. If we think about this sort of as a TLS4, 1-octet version, then that's sort of just like non-backwards compatible, and we can do all the stuff the way that would make sense without this historical legacy. So it kind of makes some sense for new applications.
Valery Smyslov, LS Plus. My question is somehow related to previous. Is it a completely new protocol incompatible with TLS 1.3, or can we do it somehow negotiable? Whether the compact encoding or full encoding is used so the CTLS clients can talk to full 1.3 TLS servers?
Yeah, there are a couple of angles there. I think one angle obviously would be to have, you know, to have a like non-CTLS client hello followed by the server sending you CTLS. Another angle would be, and this is the one Karthik and I talked about, is to have sort of a translating device who only gets who doesn't get any of the keying material, but only gets the AAD keying material, and that can do the expansion internally. So we looked at a bunch of options.
Well, but probably the encoding itself can help. For example, if you put some magic value in, I don't know, version field that will tell that it is compact encoding, then no translated device is needed. And so okay.
Thank you.
All right, so we got to cut the line and let's keep it succinct, please.
It's AGL, I think, is next.
So I think you basically just said this, but if you want to keep yourself honest and convince yourself that this is a security irrelevant transform, implement it as untrusted shims, like on either side.
That's in fact the implementation that you have is that.
Okay.
Yeah, so the numbers on the slide are from an implementation we did in Mints, which is implemented in exactly that way. There's a compression layer interposed between the handshake and the transport.
If you do that, I think you have very good confidence that you haven't broken the security.
Gary Mondi, Qualcomm. You mentioned the latest version of the document, predetermined cipher suites as a potential compression candidate. Do you have any thoughts as to what a server would be expected to do if a client tries to actually negotiate with a predetermined cipher suite and the server does not know what that client's cipher suite is? Would it be dropping back to a TLS, DTLS handshake, or would it?
I think in that case it would fail.
It would fail.
I think so, yeah. Richard may have some other thoughts, but I think that you can only get the maximum compression you get is if like basically you have prearrangement.
Yeah, I mean, it's like the usual compression trade-off. Like the more you pre-negotiate, the better compression you get. And in this experiment that we did, we kind of turned the compression dial all the way to nail everything down and see how far we can get it. I expect, when we look at, the comparables in ad hoc, there's like a little bit of negotiation in there. I think they have like a couple of cipher suites they can negotiate. And so I think as this develops and we have some discussion, I think this will go on in the Lake working group. But as we have the discussion, some of that will be added in, but probably in using some of these optimized encodings that Ecker mentioned to do whatever little bit of negotiation we need to make this work.
Do you mind if I ask another question?
No, I think we should need to take it to the list. We got some other presentations.
So. I'll be around after this if people want to talk.
Hello, I'm Douglas Stabile from the University of Waterloo, and I want to talk about our draft on design for hybrid key exchange in TLS 1.3. Next slide. So just as some background, there's been a variety of interest in using multiple key exchange algorithms in the handshake as part of a transition to post-quantum crypto, and a variety of internet drafts and implementations over the past few years. The idea to focus on key exchange rather than authentication is that we're concerned that quantum computers could retroactively decrypt, but they can't retroactively impersonate parties. So the goal here is to develop a framework for using multiple algorithms simultaneously. Next slide. One thing we're not trying to do is pick a particular post-quantum algorithm. We'll leave that to the NIST post-quantum standardization process. Next slide. So at the last IETF meeting, Chris presented on our behalf the first draft, which contained a menu of design options on several design aspects. So how to negotiate which algorithms and combinations should be used, how many algorithms can actually be combined, just two or more than two, how to transmit the public key shares, and how to combine the secrets. The feedback we got from the working group was to avoid changes to the key schedule and to try to simplify the menu of options and down to a couple of candidates. Next slide. So that's what we've done. In the draft today, there is still the menu of design options, just so that's kind of there for reference. We've got two candidate instantiations, which I'll talk through today. The first option kind of directly negotiates each algorithm and separates the key shares. The second one kind of follows what some of the implementations have been doing, having code points for each defined combination. We also added a new KDF that was suggested by someone in the mailing list. Next slide. So in the first instantiation, we're kind of taking a proper approach where everything is done separately. So this follows an earlier draft by William White and others. The algorithms are negotiated individually. So there are new named groups called hybrid marker 0, hybrid marker 1, which don't actually mean anything in themselves. They're just pointers into a hybrid extension where each marker is mapped onto the groups or key exchange methods that are meant to comprise that. So each party can suggest as many combinations as they like, and they're indicated with these hybrid markers. And we can allow multiple algorithms. We've put a maximum of 10, but there's no reason that you couldn't have more than that. Next slide. So once those have been listed in the negotiation, we have to convey multiple key shares, one for each algorithm. So in this approach, we use the existing list of client key shares, send one key share per algorithm, and so we don't require any new data structures. This, at least in the client hello. The server hello, as it stands, doesn't allow for multiple key shares to be transmitted. So we have to kind of hack that in. And so the way we've put that in the document as it is to have a data structure encoded inside of the existing key share server hello that basically concatenates these key shares. Next slide. Then we have to combine the shared secrets. So once the key exchange has been done, we have the cryptographic keys. And in the approach that we've got here on the slide, these key shares are concatenated, fed into a KDF, and then the output is put into the TLS 1.3 key schedule in the place of the existing Diffie-Hellman key share. So concatenate, KDF, and then use it as it is now. Okay, so that's the first candidate. On the next slide, there's the second candidate. So this follows more what some of the implementations have been doing. And this is a simpler approach from an implementation perspective. You define new code points for each combination that you want to consider. So you can see we've just extended the named group enum here to list new combinations. So P256 with post-quantum algorithm 1, whatever it ends up being, P256 with post-quantum algorithm 2, and so on. And there's no internal structure to these code points. It's just a new code point. And then on the next slide, to convey the key shares, then we just convey the concatenated public keys for each of these new code points. So this really requires no changes to the structure of negotiation or any negotiation logic. Everything is just a new key exchange method. Next slide. So to compare these, the first instantiation, we have new negotiation logic and a new extension to convey these, the list of algorithms. But it doesn't require any change in how the key shares are conveyed, or it doesn't require multiple groups to be defined for each combination. Whereas in candidate instantiation 2, there's no change in negotiation logic or protocol logic. We had this combinatorial explosion of named groups, and you might have to send duplicate key shares. So if you want to advertise P256 with algorithm 1 and P256 with algorithm 2, you have to send 2 P256 shares. So those are kind of the trade-offs between these two instantiations. Next slide. So we'd like some feedback on how to proceed, either of these options being more appealing, and then what the procedure should be for a document like this.
Hey, thanks for doing a great presentation there. We have 10 minutes for discussion.
Jonathan Hoyland, Cloudflare. So obviously, as someone who did one of the formal analyses, I'm very against changes to the key schedule. I think actually your first approach could be wired into the key schedule in a sort of standardized way. And given the other things that we want to do with the key schedule, we should just first work on standardizing how to inject new keys into TLS.
Okay, so we have a few options in the draft.
I've been reading, I've been discussing it with Chris.
Yeah, okay, happy to talk more.
Adam Langley, option number 2. It's not worth all that complexity to save 32 bytes. Don't mess with the key schedule. We've already shipped it. Works great.
Okay.
Yeah, Ben Kaduk. So, I mean, in terms of the trade-off, I mean, I know Adam already told us what to do, but, you know, it's sort of a question of if you have a pretty good idea that everybody is going to be doing the same sorts of things, same sorts of algorithm combinations, then it's pretty clear. If it's like totally out there and you're going to be trying all sorts of random combinations, that's when you really want to be doing it independently. It's basically the same question as what a TLS cipher suite means. And we took some of that out for TLS 1.3.
Great, thanks. Yeah, I don't think it's clear at this point how many algorithms there will be coming out of NIST, whether it'll be 2 or 5. They haven't given indications yet. So that may affect the decision going forward.
Watson?
Watson, Cloudflare. I think we are not going to have a large number of algorithms that are being combined. Most of the time, it's going to be P256 or Curve 25519 combined with some post-quantum algorithm. And there's only going to be sort of 2 algorithms being combined. So I think that motivates picking the second option for how you do the combination. You just declare a hybrid cipher suite.
Okay, thanks.
Yeah, thanks. Martin Thompson, I'm going to speak for candidate 2 as well, and option 2. I think that's been implied in the discussion that you got here, but I want to say that explicitly. One of the things that you kept saying throughout the presentation that irritated me a little bit was you kept saying concatenation, which is not necessarily injective. So we want to make sure that's crisp in people's minds, because that's kind of important if we talk about things that aren't simply fixed sequences of octets. Now, I think most of the things that we operate on use that as both inputs and outputs, but we need to be very clear on that point. So thanks.
Thanks. Yeah, for the key share, we've definitely got a data structure encoding. For the shared secrets, right now we're just doing actual concatenation, but with the proviso that this doesn't make sense if they're not a fixed length.
Marco, NCSC. I'd like to thank you for bringing this draft to the working group. I found it a useful reference. I'd like to speak in favor of option 1 here. I think it's good to have the informational document that describes the different ways of doing these hybrids and the pros and cons of each. So I think that's useful. I can see scope for both of these actually, but I think doing one in the first place would be good. I'd also like to speak in favor of trying to keep options in there for having the hybrid designs to be as general as possible, so possibly incorporating more than 2 algorithms into the hybrid, and the possibility of combining classical algorithms as well as just post-quantum algorithms in there. Thank you.
People have been assuming that NIST will only approve 2 algorithms or 3 algorithms. That may be the case. However, each algorithm that they've been under discussion have multiple parameter sets, and we're likely to want each parameter set to be treated separately. Instead of only having 3 algorithms, we might have a total of 12 algorithm parameter set combinations, and that should need to be kept in mind.
I think Watson said what I was going to say. I was just enjoying standing up.
Yeah, so Martin Thompson, in response to Scott there, I think this is something that we would ask, I would want us to ask the CFRG to address, because I don't want to have this explosion of parameter sets. I want 1 option, preferably, maybe 2. And that may be 2 different options, and there may be different sets of options for different use cases, but ideally it's 1, maybe 2 for the for any individual use case. That make sense?
Yes, NIST always underspecifies these things, and where the IETF has not then finished the specification, bad things have occurred.
Right, right. And I mean, PSS is an example of that, and it's pretty hard to use, and that's got like 2 parameters.
Yeah. When it finally happens, we'll have to nail down all the parameters. But even so, I'm not worried about a combinatorial explosion, because the first element of this tuple is always x25519. Because who is doing modern stuff and still using P256?
Yeah, I agree.
Thank you, Douglas.
Hi, so this is, as mentioned, on the topic of ESNI split mode. Next slide. So I'm going to use the term load balancer here. This is maybe an idiosyncratic usage of the term, but the load balancer is this thing in the middle that's doing the splitting or the forwarding or the proxying. I'm going to call it a load balancer. I am particularly interested in a kind of load balancer that I call an SNI proxy. So that traditionally has been something that inspects the SNI and then forwards to a backend that is determined by its by the connection's SNI. And the nice thing about SNI proxies is that they don't terminate TLS. So they're, in a sense, they're the highest point in the stack that doesn't terminate TLS. It's the most information you can get while maintaining end-to-end TLS. Next slide. So the motivation for this is split mode ESNI. And I'm going to draw a distinction here that I don't think is clear yet in the ESNI draft between partial and full split mode. So the key difference here is that in the ESNI draft, you must know the ESNI private key in order to reply and formulate a working server hello. But if you have a variety of backends and they all have this private key, then you have a widely shared private key. So for example, if you are operating a large commercial service, your adversary could simply sign up for your commercial service, learn the ESNI private key, and then use it to decrypt SNI on the wire. So for that reason, we would ideally like to have full split mode where backends do not have the ESNI private key. But under the current specification, that means that they can't answer in the server hello. Next slide.
Hi, Stephen. So partial split mode is kind of the new term you're introducing here, right? Is that a real thing that we'd ever want, or is it just like
the ESNI draft uses the word split mode to describe both of these things in different places within the draft?
Personally, I never considered that middle line as something that anybody would want. And if it's covered by the description, then maybe the description is not sufficiently precise.
Maybe this is going to be a rat hole, but I'm also surprised by this. I thought that the way I'd written the specification was designed around full split mode, but it's of course possible I made a mistake.
So if I remember the text correctly, the current ESNI draft says that you can implement split mode either using the encrypted Z hack or by sharing, pre-sharing the ESNI private key.
It's possible I said that was dumb if I did.
Yeah. Ben Kadek, it sounds like everybody only wants full split mode, so maybe we should just make that change and not worry about the distinction.
Next slide. So this is not the only case where somebody has had a proxy in the middle of the connection and wants to send some information along with the connection to the backend. And the major case where this is done already is in the proxy protocol, which is almost entirely used just to inform the backend of the true client IP address, which is no longer visible to the backend. But it can, and it has been extended to incorporate lots of other information, especially actually when you are terminating TLS at the load balancer. It's widely implemented and it's completely unencrypted and secure. So while we're in the business of trying to forward some secure information between a load balancer and a backend, maybe it would be nice to set up a clear path forward for people who want to do that in a more secure way. Next slide. So the proposed architecture here, which is completely lifted from the ESNI draft, is to simply use a PSK that's prearranged somehow between the load balancer and the backend to encrypt some proxy data, which is basically just a bag of data. And that includes things you need in order to answer the ESNI. If you're doing ESNI, it includes the client IP address if you would have otherwise used the insecure proxy protocol. And the backend just does some symmetric crypto to decrypt and use that info. So this is what the draft says currently. And in response to the draft, there was some very thoughtful and detailed analysis on the list, and a couple of other architectures were proposed. Next slide. So one proposal, which I believe was made by Stephen Farrell, this is my attempt to capture a proposal by Stephen Farrell, is to simply do TLS in TLS. So rather than specifically encrypting the proxy data, open a new TLS section between the load balancer and the backend, write the proxy data into that stream, and then write the client hello and everything that follows from the client. And similarly, the downstream responses from the server would be in TLS, would be decrypted and forwarded to the client. So this is very clear. I think it's the cryptographic properties are nice and clear, but it is computationally intensive. We're spending a lot of time encrypting ciphertext again.
Jonathan Hoyland, Cloudflare. In putting a TLS session inside a TLS session does not give you clear cryptographic properties. You have to bind them together using exporter keys on the outer one and then some magic on the inner one if you want to actually get the security properties you think you're getting. Yeah, it's a lot more complicated than you might think.
Christian Huitema. Ben, there is similar work going on in the Quick Working Group on the load balancer protocol. I don't know whether you're following that.
There is a draft in the Quick Working Group related to load balancing. I think eventually we are going to have to square these two concepts. I think that the load balancer draft in the Quick Working Group so far I think addresses largely separate issues, mostly related to connection IDs and migration.
That is correct, but I mean, they're related.
Okay.
To pay on. There was some theoretical research, I don't know how else to say this, that was done before Quick was announced to the IETF about intermediary assisted packet loss stuff, which has many very similar properties, and I suspect that you should look that up.
Okay. I will try to look at that. Next slide. So another alternative architecture, this is my attempt to capture a proposal described by Martin Thompson, is to use an oracle to decrypt the ESNI. In the simplest implementation, that would mean that the connection is forwarded to the backend completely unmodified, and then the backend contacts an oracle and asks it to decrypt the ESNI information. This is nice and clear, but it's probably too slow to implement in this literal way. You'd really want what I would call a push oracle. You could imagine implementing this with HTTP2 push, but this becomes a really complicated and potentially flaky setup. So next slide. My questions are, should we be pursuing this at the IETF in TLS, especially given that we've also been talking about what's appropriate to go inside the ESNI draft? In my view, there is an interoperability question here. There is essentially existing work in the form of the proxy protocol for communication on this link that's not secure, and I think it's worth trying to do better, and I think that the use case in ESNI is important and worth trying to serve. And if people do think that there's work worth doing here, then there's an architectural question. Which direction should we be going here before we really hammer out all the details?
Martin Thompson. I'm not going to get up to talk about the details of the protocol, but I think we also have a third question, which is an organizational one, which is where work like this happens. If we have a quick working group that is addressing a very similar use case, it seems to me like this straddles this working group and that one. It would not surprise me if there were other people that had similar uses. Maybe this is something that needs to go to sec dispatch or I don't know.
Gen area.
Let's put it in gen area. Yeah, I'm sure Alyssa would love you.
Yeah, I'm generally enthusiastic about this. I haven't thought about the details that carefully, so I'm not willing to opine on them yet. Martin's probably right that we do need to think about where this ought to go. Perhaps I see an area directors, that's very helpful, but perhaps some of the considerations ought to be what the how much is a security protocol versus like an application information protocol. My suspicion is it's actually a security protocol based partly on Jonathan's comments, but other things like that, that if we don't think about the security aspects, we may be sad people, but it may also be the case that the security questions are well isolated and can be, handled separately. That is, have a secure transport and then like figure out the binding mechanics and then just stop. So I don't know yet, but it might be useful to work out some of the other cases of what kinds of information you might want to carry in this protocol, and then we'd have some sense of where we were.
I do know that there were a couple of IAB members in Mike line, but yeah, this seems like a question the IAB and the ISG should think about, where to do this work so we don't duplicate efforts.
Jonathan Hoyland, Cloudflare again. I do think that there's been 3 drafts and there are 6 currently adopted drafts that all do basically a very similar thing from a theory level in terms of binding stuff into TLS. So maybe as a working group item, we should start considering how instead of doing exporter keys, we do some sort of importer keys, and not directly, but there are a bunch of drafts that try and do this. We should just solve it.
All right, Stephen. Yeah, so I think we should standardize a solution. It should be, done. We shouldn't do something stupid, basically. It's not like that would ever happen. And I don't yet know what architecture I'd recommend. I think I'd need to know more.
Eric Nigro and Akamai. Yeah, this topic has come up a few times. I remember even, I think in the first HTTP workshop, this came up as a big topic because the current proxy protocol, or the current proxy protocol isn't really, with air quotes, isn't really standardized. And there are plenty of cases where vendors will ask for implementation of it, but the lack of security here does not make it appropriate in a bunch of cases where it's being used. But I think finding something that is efficient enough that's probably closer to your first one is going to be important, because if we just do this but totally change the shape of it, no one's going. It may be that it'll be hard to switch implementations away from some of these current insecure use cases.
Okay, thanks. I think the outcome here is to talk to the ADs and figure out if there's some grander plan that we can figure out what to do with. All right.
Thanks.
Yeah, back to the plan of coordinating between the ISG and IAB. We'll put it on the agenda to chat on Friday.
So Eric Nygren I'm going to be talking about a proposed HTTPS service record. Next slide. The topic of this conversation, or the motivation for this, came out of a number of conversations that have been going on. It came out of the ESNI keys discussion, where as we're looking at having this ESNI record, which would be a new record for clients to go look up, a lot of complexity around how to handle things like multi-CDN and proxies and other use cases kept showing up in it. And ESNI trying to solve that as what ends up being kind of a more holistic problem, solely in the context of ESNI, started creating both either a complexity risk, but also a composability risk of how, when some of these next issues start coming up, are we going to have to try to cram those into that ESNI record, or maybe we should take a step back and look at some more things more generally. One comment on these slides is that these slides are from before I presented in HTTP BIST, and there have been a number of conversations since then. And I think one of the big open questions that's come up is how much it makes sense to go and generalize some of this beyond just the HTTPS use case. And I'll talk a little more about that later. But some of the top things, at least on the HTTPS front, that there's a desire to address right now in parallel, is the encrypted SNI keys that we've been talking about here, transport protocol, and how do clients start using HTTP3 and QUIC without having to go through a redirect through a legacy TCP protocol is another one that comes up. And how do we kind of bootstrap into that via DNS, especially if there are better end up being better privacy properties if you can go straight to QUIC rather than having to go through TCP. Indicating origin default that an origin defaults to HTTPS, so that we can just have that when
someone puts a bare name into a browser and types in example.com, being able to have a clear way to say, hey, this goes straight to HTTPS without having to do that redirect through clear text HTTP and having a more secure default. Next slide. So the approach here is to look at things that is having a single new record that browsers can resolve in parallel with the clients can resolve in parallel with the quad A. In particular, this is not really browser specific, despite what this slide says. But also look for something that's has reasonably good usability from an operational perspective and has some performance optimizations baked into it. So, which we've spent a lot of time on the ESNI key side of how do we make this so that doing this extra lookup minimizes the performance impact and overhead, number of round trips, but also having it be extensible enough so that when we want to handle the next case beyond the few that have been identified, that we can add this in a reasonable fashion. But also something that is compelling enough to convince clients to implement it. Because when talking with the DNS op group over the years, they have a specific issue around the Zone Apex problem, which they built the SRV record to address a number of years back. And there's some frustration on the DNS side of, hey, we created SRV, we kind of meant it to be for the HTTP use case, client never really started using it. So something that can break this chicken and the egg of okay, we're going to introduce a new record, but convince both enough clients to implement it, but enough server operators and DNS providers to implement it, may help get past some of the standoff here. But also gives, and I think another goal is look at is there a way to especially as clients start using DO or other things, is there a way to have more secure defaults we can move to help close out some of these kind of insecure by default straight to HTTP and then having to upgrade up style use cases. Next slide. So the general approach here is you can look at it as being somewhat similar to extensible SRV. It's that, and a reminder here is that within DNS, if you get a bunch of individual RR sets back, there's no way to necessarily associate them. So if you do a resolution for a ESNI record and you do a resolution for an A record and a quad A record, there's no way to determine that those actually came from the same source. In a multi-CDN case, some of those may have come from one CDN, the others may have come from the other CDN. So fundamentally what you need to do is have something where you have a single resource record that kind of binds a number of attributes together. If you look at even SRV does this by saying for this given name that I'm trying to look up, here is kind of the actual server name and the port number for that, and associate that together because you may have some server names which implement some ports and other server names that implement other ports. So HTTPS service basically takes that and extends that and allows additional attributes to start getting associated onto that. In the particular case for TLS, ESNI keys becomes one of those, but we could potentially see other things being associated on there in the future. Next slide. I won't go into great detail in this here. This is probably more, some of these details are being talked about in more detail in the DNS op and HTTP BIS. There are two forms for this. I won't go into great detail on this form, but next slide. The alternative services form is the one that the ESNI keys would come into play for the HTTPS use case. There's within it, you have a service domain, a service name that indicates what the name is. So, for example, svc3.example.net would say that if you go to svc3. The top line here would be, for example, that if you're trying to get to svc.example.net, you should use svc3.example.net over QUIC to port 8003 on QUIC with a particular set of ESNI keys. Or you could go and use svc2.example.net over HTTP2 on a different port with potentially a different set of ESNI keys. Next slide. So one of the questions that's come up on list is, as well as in conversations, is what's the relationship of this to the the ESNI record that was proposed. And I think there's a third example that or a third scenario that's not covered here. So kind of at a fundamental, I think it makes sense to separate out the ESNI key format itself from the way we're distributing it through DNS, and look like some of the most recent draft versions at least pull some of the DNS extensions out of that record. And then the question becomes, what do we do about the DNS records here? I see there being a few different options here, one of which is to say that you have a per application protocol binding that would describe how you would want to use ESNI keys for a given protocol. So for HTTPS, we could say, go use the HTTPS service record, and then there could be a generic, either simpler binding that says, hey, go use the ESNI record. Another option here is there's been some interest of saying, okay, HTTPS service seems useful for other use cases. Maybe it should be generalized to not just be HTTPS specific, in which case you could have that more generic HTTPS, or that more generic DNS record use case could cover the ESNI case as well and incorporate support for ESNI keys, and therefore potentially eliminate the need to have a separate ESNI record. Next slide. Next, in terms of next steps, when I wrote these slides, I thought that HTTP BIS, what we're going to be talking about this afternoon, might be the best home for adoption for this. After talking into DNS op and talking to some of the chairs, it may actually be that DNS op is a better home for that, and the DNS op and HTTP BIS chairs are talking on that front. There's a place in GitHub where we've been working on this until we get it adopted in a particular place. On the name server side, on the DNS side, there's been interest in this, especially because it solves some other problems they've been interested in. So there's a bind9 private type implementation that got done by Mark Andrews, and in the hackathon, someone did an unbound implementation.
Alessandro Ghedini, Cloudflare. If I understand this correctly, the client would have to first resolve the HTTP SVC and then do another resolution for the alternative name.
And there's a bunch of optimizations proposed in the draft. So if following the optimizations, the client would do resolutions of the A, Quad A, and HTTPS SVC in parallel with each other. And similar to some of the cases in ESNI, if things go right, once you get those records back, you shouldn't have to do any more in the cases where they all point to the same thing and there's not a multi-CDN use case showing up. One of the kind of open issues / questions has been, does it make sense to kind of follow the path of the ESNI record and inline, or have a way to inline the A and Quad A record straight into the HTTPS service record? There are a bunch of upsides and downsides for that. For example, not inlining them and having them be separate makes some of the proxy use cases like Proxy Connect work a lot more cleanly because it allows you to separate some of that out. On the other hand, inlining it helps for performance, and inlining it also may reduce some of the complexity of client implementations.
Right. There was a proposal for ESNI for the multi-CDN problem. And, well, there were two proposals. One was embedding the addresses in the ESNI record, and the other one was like advertising a separate name or whatever. And the reason the second one wasn't picked was that it would require two resolutions, and that wasn't like a good idea.
And if you structure, and there's some recommendations in the draft, if you structure things right, you do have I think there was some discussion on this and some experimentation on this on the ESNI side. You can get cases where if you do those in parallel, you may be able to get a reasonable enough hit rate that it's not that bad performance-wise.
We got about 10 minutes left, folks. Thanks for presenting this. I'm certainly more than happy to outsource the work of DNS hacking to DNS people as long as it actually meets the requirements. So I think, as Alessandro indicated, the reason we selected the current design was because we felt like that was going to have the highest probability of getting you an answer in the time frame that you needed to have to be efficient. If it turns out that assumptions are incorrect, certainly we could look at a different thing. Seems like the question of whether inlining is possible, certainly, as you say, there's no reason this can't contain inlining, so it's perfectly compatible with that, if that's the way you decide to go. I don't really understand quite the relationship between TLS, which would be the first consumer of this, and DNS app or whoever would be the ultimate producers of it. And I want to make sure that that relationship was well specified and that we didn't end up backed up way behind something that was very complicated. Or not complicated, that was going to take a very long time in another working group because we certainly want to deploy ESNI relatively rapidly. So those would be my concerns. But if we can manage an efficient process on both sides, certainly having something which was not designed by TLS people to be shoved in the DNS would be a superior outcome.
Hi, Eric. Thanks for presenting this. I'm a little bit unclear what's specific to HTTPS this record has. It seems that it applies to TLS generally.
And I think that is that's probably been the biggest side effect of feedback on this so far, is that it makes sense to generalize this. And I think the exact question will be, how does it make sense? Like, what is the right form of generalization of this? But I think if this got adopted within a work, and that was one of the reasons why DNSOP may be a more attractive place to adopt this, is that it would be that we could go and look at what is the right way to generalize it there, such that for that we don't have that we can minimize the performance impacts, deal with a bunch of these corner cases that were coming up in the ESNI design, but do it in a way that covers a bunch of the other cases. And then there may, in addition, may have value of being a kind of subsequent patch or thing on it saying, for the HTTPS use case, here are some additional ways to use it, possibly as one HTTPS RR name and one HTTPS specific RR type and one more generic RR type that have roughly the same form, or have the same format, but have some additional semantics layered on for HTTPS.
I guess more specifically, my answer is, which part of this is only HTTPS? It seems that it's only the alt SVC.
The things that are HTTPS specific in this are that we use the alt SVC formatting for it, and that treating that not using the underscore labels for the HTTPS 443 scheme, so that you can just to deal with some of the wildcard use cases for it, as well as the HSTS style proposed default behavior.
Okay, thanks.
Adam Langley. So I think you started from sort of an SRV record, and that's why it looked to me that the sort of redirect host is mandatory in this textual format. But why do we need that? Why do we need to name, say, the CDN? Like so I'm assuming you'll stuff the IP addresses in there because that makes sense. But I don't understand why it's not just a blob of key values.
In particular, you do need to get the IP addresses, or some way of tying to something that'll give you IP addresses, or have the IP addresses directly in there, because to handle things like the multi-CDN use case.
Well, you don't know, because let's say that I've just got one server. Like, you can look up its A record and you can look up its HTTPS SRV record, which gives you a bunch of other information. Like, I don't need this redirect name, and like I wouldn't need IP addresses. But obviously, if you've got multiple CDNs, then sticking IPs makes sense. Mm-hmm. But I don't understand why this host name field is mandatory in this record value.
And so one thing that host name field can be in the draft is it can just be a dot, which says it's the same as the record.
Oh. Okay, so it's already optional. It's just textually prioritized.
Yeah, there's basically a way to say use a specific form in that case.
I would textually demote it, but okay, thank you.
Tommy Pauly, Apple. So
Thank you for sharing this. I know we've already talked, but I'm definitely in the camp of people who says this should be a generic thing. I think that does make more sense. So just +1 to all of that. Yeah, and I think just with regards to how much is inline versus somewhere else, maybe one way of kind of breaking that up, because I think there are a lot of other things I would like to see that maybe aren't appropriate to actually fit inline. I'd like to get those somewhere else, but maybe we could have a split of things that are shareable between multiple names, multiple records that is external. And that actually mitigates some of the lookup cost, right? So if I had a CDN deployment that had, so let's say I want to actually be able to use this for like DO server discovery, saying like, these are the right things to do for that. And if those are all sharing properties between names, then that's something I can go fetch kind of a generic CDN configuration from some name that you allowed me to look up through this. But if you have a specific key for just that particular name, then that stays inline. So I think this mechanism is a really great way to allow for this extensible vocabulary going forward.
Right, and I think to some of the why do we have names rather than IP addresses also goes to that, because the other, like an example of that case would be if you have, if you want to advertise both H2 and HTTP 1.1 and Quick for a set of A and Quad A ad records, you may, like combinatorically, you otherwise end up with, and I think you end up with a potentially huge set of things, and having that indirect level of abstraction helps address that. And I think like for the ESNI key itself, one of the questions is that, do you inline a base 64 of that, or do you have a name reference, or do you allow either case? Do you allow either case? Because I think there's that trade-off between the performance impact of doing indirection versus message size, especially in the face of caching.
Right, and then if you have like totally unique ESNI keys for every name, then have them inline. But if you have a way to derive them generically, put it elsewhere. Thank you.
Lorenzo Cludi, +1 to making this more generic. I think that sort of argues against putting in HTTP BIS, but could be either in DNSOP or TLS. I wanted to point out maybe that, you know, perhaps everyone's aware of this already, but like the ESNI key is a property of the IP address, not of the name. So it does seem more sort of straightforward that the IP address be in here, because otherwise you basically, when you do a parallel implementation, you do an A and a Quad A and a service record lookup. But if you're unlucky and the Quad A you get the Quad A for a different CDN, then you're like, oh, wait, you have to basically walk the intermediate CNAME chain of the HTTPS service record, and then do another lookup for a Quad A for the name that you had. And so that the CDN operator is good, or you get lucky, it's efficient, but if not, and it's very complicated to implement on the client. So +1 to putting IP addresses in there, I guess.
Mike Bishop, Akamai, just making the observation that this is an outgrowth from having the alt service DNS record, which is why it's in the same repo. And that alt service is applicable or could be applicable to other things than HTTPS, but hasn't been defined for that. And so this is a step in that direction and could eventually be generalized, but I think we'd have to figure out what it means to have an alt service record for something that is not an HTTP origin.
Dan York, Internet Society, but not speaking for Internet Society. So to Lorenzo and Adam's case, I'm somebody who wants the domain name in there because I'm from the DNS side and I want to use this for the CNAME at Apex fix to be able to point from foo.com over to a CDN in some case. So that's where I'm looking for that. My question for you though, Eric, and thank you for presenting this work in these places and doing all this, this will require client implementation across all the clients for this to work correctly, correct?
Correct. Okay. I think that's and similar to the ESNI record would also presumably need the same thing.
Okay. And I've seen a number of people doing prominent clients standing up here, but are you the co-chairs, are you, not the co-chairs, the authors, are you involved with talking to those about getting this into their thinking?
We've been having conversations with a number of, certainly some browser clients. Haven't yet had as many conversations with non-browser clients. I think at least one conversation, it was clear that when you start having a fairly rich stack that provides an abstraction like an HTTP abstraction or a TAP style abstraction, that you can fit this sort of thing into that abstraction well. What becomes trickier and may also be trickier with ESNI as well, with the ESNI record, is when you start having a much closer to the metal style set of abstractions, and you're still dealing with things like get DNS by name and connect and such, that it does add a lot more complexity to that class of client.
Okay, I mean, and so I hope other people who are here who have clients that could consume this will be talking to you. My one concern, just looking at it, is that it is capable of solving a good number of different use cases. And with that comes the complexity of implementation that I think there's, I guess, a question in my mind around the scope of it and how many of those use cases we really try to solve with this piece here. But
Right.
thank you for doing this work.
And I think that's also a balance on how general to make it, because the more general it starts becoming, as we've seen with many things here, the more risk you start having of having it be way too complicated. On the client side, one reason why I'm somewhat less concerned about some of the client complexity is for enough of these use cases that want it, having robust client libraries that people can use that handle things like TLS cert verification well and DNS and connection management well is going to become increasingly important, because a lot of the people who do the hey, I'm just going to use some of the underlying primitives directly without really understanding them well, there seems to be an increasing risk as those primitives start getting more and more complex that they won't do they won't understand the caveats and, for example, won't do same TLS server cert verification.
We're out of time, basically. I should shut up. Yeah.
Thank you, Adam. Thank everyone for showing up. We had some different presentation requirements this time, so please let us know what you thought about the presentations this time. Just tlschairs@ietf.org. Thanks.
Blue sheets. Blue sheets, where are the blue sheets?
So the thing is turned off. I will have